Today, we're diving into the world of material science to explore MatterGen, an AI tool developed by Microsoft Research. It's got the potential to change how we discover and create new materials, and that could have some pretty big implications for different industries. We're basing this deep dive on a Microsoft Research blog post and an accompanying research publication. They explain how MatterGen works and showcase what it can do in detail.
Discovering new material has always been a pretty challenging and time-consuming process. It's like trying to find a needle in a haystack.
Yeah.
Traditionally, scientists had to conduct numerous experiments in the lab, testing various combinations of elements and structures. This could take years and consume vast resources.
And even with computational advancements that allow for screening massive material databases, finding materials with specific properties remains a hurdle.
It does.
MatterGen takes a completely different approach, though. It doesn't just search through existing materials. Instead, it designs new materials from scratch based on what you need.
That's right.
Imagine telling an AI, I need a material that can withstand extreme temperatures, is lightweight, and incredibly strong, and then it generates multiple viable options.
That's the idea.
MatterGen is fascinating because it's a generative AI model. Similar to AI that creates images from text prompts, it operates on the 3D structure of materials.
Exactly. It starts with a random arrangement of atoms, and then using a process called diffusion, it refines the structure step by step. The AI adjusts the positions, types, and arrangements of atoms based on the desired properties until it generates a stable and potentially viable material.
The results are impressive. MatterGen boasts a 78% stability rate, meaning the materials it designs are highly likely to exist in the real world. Also, 95% of the structures it generates are very close to their ideal form, demonstrating the precision of the design process. This level of performance goes beyond what previous generative models can do and marks a true advancement in the field.
That's one of the key advantages, going beyond the limitations of existing databases. It doesn't just recombine known materials, it generates truly novel structures. This opens up a vast realm of possibilities for discovering materials with unprecedented properties.
The research paper includes several case studies that show off what MatterGen can do.
They do.
One focused on finding stable materials within a specific set of elements. MatterGen outperformed traditional methods. It found 5 new, stable structures in the VSRO chemical system, while the best traditional method only found 2. This demonstrates MatterGen's potential to uncover hidden gems even in well-explored systems.
It does. Another impressive capability is designing materials with specific symmetries. Symmetry plays a crucial role in determining a material's properties, and most generative models struggle with creating structures with high symmetry. MatterGen successfully generated stable and novel materials with targeted symmetries, demonstrating its ability to control this crucial aspect of material design.
The research also demonstrates MatterGen's ability to target specific magnetic, electronic, and mechanical properties. For example, it generated materials with a high magnetic density surpassing a specific target value. This has significant implications for applications like permanent magnets, where maximizing magnetic density is critical.
Yes, and let's not forget a real-world challenge, designing magnets with low supply chain risk. Many high-performance magnets rely on rare earth elements, which are prone to supply chain disruptions.
Of course.
MatterGen was given the task to generate magnets that not only have high magnetic density, but also a low supply chain risk score based on the Herfindahl-Hirschman index.
And it was successful.
It was. MatterGen successfully generated materials that met both criteria. What's remarkable is that the elements used in these generated magnets differed significantly from those in traditional high-performance magnets, effectively avoiding those associated with supply chain concerns.
So that means we could potentially create high-performance magnets without relying on materials subject to geopolitical and economic instability.
Right.
Let's take a look under the hood and see how MatterGen accomplishes these impressive feats.
The research publication provides a deep dive into MatterGen's architecture and the diffusion process behind its generative capabilities. At its core, MatterGen utilizes a novel diffusion model that operates on the 3D geometry of materials. This diffusion process is specifically designed to handle the unique characteristics of crystals like their periodicity and intricate symmetries.
So in practice, how does this diffusion process work?
The process begins with a random arrangement of atoms. Imagine a digital melting pot. The AI throws in a bunch of atomic ingredients without any predefined order. Then MatterGen gradually refines this chaotic structure, adjusting the positions, types, and arrangements of atoms based on the properties we want.
And the research mentions a joint diffusion process. What is that and why is it significant?
The joint diffusion process is crucial because it treats atom coordinates, atom types, and lattice structure as interconnected entities. That means rather than separate elements. This allows MatterGen to consider the interplay between these components, resulting in more stable and realistic structures.
So the AI is considering everything, ensuring the generated materials have a higher chance of existing in the real world.
It is.
To explain how MatterGen works, the researchers used an analogy. They compared it to an image-generating AI that creates pictures from text prompts. Can you elaborate on that?
Imagine an AI that manipulates pixels in an image to create a picture from a text description. MatterGen essentially does the same thing, except with atoms in a material. It starts with a random configuration and gradually refines it, guided by the desired properties. This process continues until a stable and potentially viable material emerges.
Are there any limitations to MatterGen?
Well, one limitation is that MatterGen currently only works with ordered materials. You see, many materials in the real world exist as alloys or solid solutions, where different atom types are randomly distributed. Extending MatterGen's capabilities to handle disordered materials would be a significant step forward, enabling the design of a wider range of materials, including those with unique properties stemming from their disordered nature.
So are there any other areas for improvement?
Another area is in generating materials with higher symmetry. While MatterGen has shown impressive capabilities in this regard, there's still room for advancement. Further research and development could enhance the AI's ability to create structures with even more complex and precise symmetries.
What are the implications of this research for the future of materials science?
Even with those limitations, MatterGen represents a significant breakthrough in materials design. Its ability to generate stable, novel, and tailored materials from scratch opens up a world of possibilities. As the technology continues to evolve, we can expect it to play an increasingly important role in addressing global challenges and driving technological innovation.
The fact that MatterGen is being released as open source software is also significant. It encourages collaboration and allows the scientific community to build upon this groundbreaking technology. We're already seeing interest from institutions like the Johns Hopkins University Applied Physics Laboratory. They're exploring MatterGen's potential for discovering novel materials for, important missions.
This open source approach could democratize materials science research and accelerate the pace of discovery. Imagine researchers around the world collaborating and building upon each other's work using MatterGen as a common platform. This could lead to a rapid increase in the development of new materials with applications in diverse fields.
What specific applications are we talking about here? What impact could MatterGen have on industries beyond material science?
The potential applications are vast. MatterGen could revolutionize industries such as energy storage, electronics, and manufacturing. Imagine designing materials for more efficient solar cells, batteries with higher energy density, and lighter yet stronger materials for aerospace and automotive applications.
The possibilities seem endless. It's like having a molecular architect at our fingertips.
That's a good analogy. MatterGen empowers scientists to design materials with specific properties tailored to meet specific needs. This level of precision and control over material design has the potential to transform industries and address some of the world's most pressing challenges.
MatterGen is just the beginning. As generative AI technology advances, we can expect even more powerful tools for materials design to emerge. This deep dive has only scratched the surface of what this technology can achieve. We've explored the incredible capabilities of MatterGen, its potential impact on various industries, and the exciting possibilities it unlocks for the future of materials science. It seems like we stand at the cusp of a new era in materials design, an era where AI empowers scientists to create materials with unprecedented precision and control.
It does. The journey of discovery has just begun, and the future of material science is filled with promise and potential.